All right, we're starting a new concept today, and it's called expected value. And a lot of the stuff we do it will almost feel like common sense. Like, yeah, that's exactly the way I thought the math should work out because of that. The idea of expected value is, I have a situation that's going to happen. What is the most likely outcome? And based on the most likely outcome, what can I expect? Again, does it mean that's what's going to happen? No, but it's the most likely. So let's do something as simple as a coin flip. If I flip a coin 100 times, how many tails would you expect? I flip a coin 100 times. How many would you expect to get?
50.
About 50. And we're going to show mathematically that mathematically speaking, that is the most likely outcome. Will you get exactly 50? No, but you're probably going to be very close to 50. I have a multiple guess test where there's 5 responses to each question. And I showed up unprepared because I didn't know it was today. So there's 100 questions and I guessed it, every single question. How many should I guess right?
About 50%.
But there's 5 responses this time, not 2. This is not common sense yet, but it will become common sense.
Should be 25.
I'm getting close.
20%.
About 20. Why about 20? Because if I'm guessing on every question, I should get about 1/5 of them correct. Because there's a 1 in 5. Does that make sense from that standpoint? Okay, and we can show mathematically that's exactly what you should expect. Is that what you're going to get? Well, you might be a better guesser than that, or you might be a worse guesser than that. But the idea of expected value is I can calculate the likelihood. And where expected value is used, actually in everyday life mostly, are things like investing, insurance. Remember we talked about that last week. Okay, based on my driving record and driving history and the type of car I drive and the part of town I live in and because of everybody else, what is the expectation of what's going to happen in the next year for me driving? In other words, is there a probability that I will still get into an accident or get a ticket or something? Yeah, there's a measurable number based on everything else, and my insurance rates will be that based on what is expected. Now, what if I go that year and I don't have any tickets or accidents? Will that help me the following year? Sure, unless I'm, 17. And then I have to wait a little longer for that to really help me. But the idea, so investing, different things like that. We're going to do some of these mathematically, but I want to kind of get your brain thinking. Okay, we live in Seattle, and we have a construction company. And one thing about construction, we might be building new homes, doing things. There's certain things you don't do in the rain. Construction. Okay, I've had a couple different remodels on my house, and if it rained, there's nobody working. In fact, they're not working after the rain. Things have to be dry. There are certain things you cannot do in the rain, and one of them is, put on a new roof. Pour cement. So we have a construction company in Seattle, and if we work today, this is how much money we're going to make. If we don't work today, we're going to lose money because of bills and debts and things going on. The probability of rain today is a certain value. Every single day of the week, all you got to do is check the weather report. It'll tell you exactly the probability of rain. You agree? So I'm the construction company in Seattle. What can I expect to make? Well, it has to do with the probability of rain is exactly the probability that I'm going to lose money. The probability of no rain would be the probability that I'm going to make money. And when I put the two together, I can say, this is what I can expect. Now, think about it on a daily basis. Then over a long period of time, I can calculate how much money my company should make because there are going to be days where it rains and there are going to be days where it doesn't rain. Okay? I had a friend who lived in Seattle for several years. He worked for, it was Boeing at the time. He was an engineer, and Boeing settled a station in Seattle. He was there for many years, and he actually told me, he says, it rains every day. He goes, it rains 365 days a year, every year. He said, it's the amount of rain. It might only rain for 10 minutes today, but it might rain for 24 hours tomorrow. But I don't know if that's true. I've been to Seattle once and it didn't rain while I was there, but I was only there for a couple of days. But he told me it rains every day. It's just the duration of rain. Anybody been to Seattle? It's beautiful. I took my daughter to visit UW because that was her first choice back then. Oh my goodness. Anybody ever been there? Probably the most beautiful campus I've ever seen. It's a city. But what was it was too much. It was too much for her. I just say it was interesting. It was the Martha Gates Library and the Bill Gates laboratories and the Melinda Gates, Art Center. They're these majestic. Every building was $100 million building, it looked like, and every single building was something Gates. Because Bill Gates has actually given billions of dollars to the university, But it was a city. And it was beautiful, and I've never been that, it was January, I've never been that cold in my entire life. I'm wearing layers and my bones hurt. No, it wasn't raining. It's still, the humidity and the cold, yeah. I thought I couldn't live here, but it is beautiful. But, so the thing is, expected value, when it comes to things like weather, this is actually a major, major deal in a lot of situations where you have weather. San Diego, we don't actually do weather, so that's not really a thing. But places where it rains, you have to take this into account. I want to invest. I just was reading an article the other day about these things called I-bonds. You guys are too young. Your parents probably remember this. When I was growing up, a gift to a minor might be something like a treasury bill or a savings bond. You ever heard that term, savings bond? They were real popular. And it took 10 years to mature, and at the end you got it, with a whole bunch of interest. It was very popular for a long time, but you had to wait a long time. So there's these new things called I-bonds, and I guess they are directly related to the inflation. They're government bonds. You buy them. You can buy them with your tax return. You can buy them online, and they're directly related to the inflation. So right now, these I-bonds are earning 9.5%. In my lifetime, I've never heard of an absolutely safe investment. But they said, and it's locked in for 6 months. But they said in 6 months, what if inflation drops like 2 or 3%? Well, then that's what you're going to earn. In other words, there's no guarantee. And you have to leave it in there for at least 3 years. Well, and then they showed the last 2 years, there have been periods of time in the last 2 years where inflation was only at 1 or 2%, which means these things aren't worth very much at the time. So here's the question. Right now, inflation is really huge, which means it's a great investment. What is the likelihood inflation is going to go up or go down in 6 months? Do you see, that's a probability question, isn't it? And all of the economists, they forecast, they estimate, they guess based on information they have now. We believe this is the most likely outcome. Are they going to be absolutely correct? No, because they're predicting the future. But they're basing it on what we know now. This is how, again, all investing is done this way. All insurance is done this way. I'm banking on the future based on what I know today. It's not an absolute thing, okay? It's sort of like in sports. One team might be a heavy favorite, but the other team still may win. It can still happen. The better team or the better player wins most of the time, but it's not guaranteed, is it? That's the thing. Everything's based on probability. So expected value, we start with something called a random variable, which is kind of an odd name because it's not really either one. Random variable is what I use to count outcomes. The most common random variable we use in statistics, we just use a capital X. It just makes it really easy. If I was counting two different things, I might use a capital X and a capital Y. We're not going to do any problems when we're counting two things. In the upper levels, you might count several things. We're going to count. So it's usually capital X, and capital X will take on any value that I can have. So let's start with something really, really, really simple. Let's say I was going to flip a coin 3 times, and we want to count the number of tails. Okay? Then what possible values, and my random variable would be the tail count. What possible values could my random variable take on then? And we usually write it like as a set. I'm going to flip a coin 3 times. What's possible?
0, 1, 2, 3.
Perfect. These are the only outcomes that are possible if I'm counting. So first of all, the random variable always represents a count of possible outcomes of whatever it is you're doing, okay? And then the next thing I'd have to do is figure out what is the probability of each of these. Well, we've actually done this already by just writing all that, head, tail. We've done that part. So if I said, here are the possible outcomes, then we'd say, what is the probability of each of these outcomes? So what we often do is we call big X the random variable, and then each of the individual outcomes we'll call little x's. Oh, then when I do things like sum of the x's, there's a consistency there. I'm not going to be changing letters of the alphabet randomly. So the little x's, we've always been calling our outcomes the little x's. Right? First outcome we'll call x1, second outcome x2, and so on. We'll continue doing that. But now here's a big difference from what we were doing. Most every time we measured something, we were doing samples from populations, because it's not realistic and that you're going to have a whole population. With random variables, it's always the population. If I flipped a coin 3 times and I wrote, there were 8 outcomes, remember? I wrote them all down. That's the population, isn't it? There's not another possible outcome. Okay, so if a random variable represents, I'm counting some situation that can occur, it's always a population because I'm including every possible outcome. I'm not sampling from that. So random variables, some of the calculations turn out to be a little bit easier. Okay, so let me go over a couple things. We know for a sample mean, we know it's the sum of the scores over the number in the sample. For the population mean, which we call mu, it's equal to the sum of the scores over the number in the population. It's the exact same formula. The difference is little n represents the number in the sample, big N represents the entire population. Realistically, when you're doing things and measuring things, people's heights, people's ages, whatever you want to measure, you probably don't have a population. Agreed? But what if we were only talking about this class? Could we talk about it as a population? If this was the only thing we were interested in, is this class? There was a nuclear holocaust. We just happened to be in a lead-encased room, and we looked outside, and the whole world's gone, and it's just us. Yeah, we're a population now. And kind of a sad thought, but it is possible we could have a population, but most of the time it was samples. But when I do have a population, the formula doesn't change. But what does change is the formula for variance. And that's what I want to remind us. So the formula for variance that we've been using is the sum of the squared scores minus the number of scores times the square of the mean over n minus 1. And most of you guys got pretty good at this, pretty fast at this. It can be a long calculation. The big difference is, if it's the population, does anyone remember the difference in the formula?
There is no.
It's just an n, which makes this formula actually a heck of a lot easier to state. So and we use a different symbol. We use sigma squared. And sigma squared is the sum of the squared scores minus the number of scores. And this time we'll use mu, the same calculation as x bar, but we're calling it the population mean. But now it's over n. Now here's why we like this. This formula simplifies so easy. This simplifies so much easier. If I had a quotient, we all know this. Anytime you add 2 quotients with the same denominator, what do? You add numerators? Is that right? So if I have a sum in a numerator, could I also go this way? Could I pull it apart? Yeah. I teach calculus and above. Do you know the single most common algebraic step we do in calculus? We pull apart quotients, which is something you learned as little kids in math. But if adding quotients does this, then I can pull apart a quotient. That means I could write this. This is why I love this formula. All right, I'm just going backwards. Why is this really good? What can I do with those ends? I can cancel them. Oh my goodness, that makes this formula so much shorter now. So the formula for population variance, which by the way, we've had no cause to use because we really haven't had a population, is just this. This is a really, really fast calculation in general, by the way. I like this, but we're going to improve upon this still. Because with random variables, when something is occurring, I'm less concerned with how many times it occurs as I am with the probability it occurs. In other words, frequency is how many times something occurred. Do you remember relative frequency was the probability that occurred? Okay, that means I'm dividing it by the n. So it's easier to speak. Well, let's go back to the exam example. So I'm saying, well, how'd you do on your exam? I go, I got 87. Out of what? Oh, okay, out of 88, out of 500, does it matter out of what? Yeah, out of what? But what if I said, how'd you do on your exam and you said 87%? Does it matter how much it was out of? You got 87% of what it was out of. Whether it was out of 10 or out of 10 million, you got 87%. That number is much easier to work with, isn't it? I don't need to know your score. If you tell me your score, then I also need to know your denominator, right? I need to know how much was your test worth. But if you told me your percent, you've already covered both of them, haven't you? So that's called your relative score. A percent is always a quotient of things. Now, this is something that in math we don't always discuss. If you're in physics or chemistry, everything you do, has units and it has, icky calculations. And in a math class, we often do an entire math class without ever using units. But understand that every time you ever drew a graph in algebra, there have to be units. There's no such thing as a unitless graph. Vertical might be distance, horizontal might be time. So then your slopes represent distance per time or speed. That would be a simple example. But in a math class, we might just say, oh, the slope is 3, right? The slope is 1/2. We don't give it units, but we're really doing ourselves a disservice when we leave units off of things, because then you get to a physics class and they hammer you over the head because you don't have the units right. But we never did it in math, because we're trying to learn how to do the math in the math class. But the term rate, when you drove here this morning, were there any rates involved? Your speed was what? Probably miles per hour? If you were in Europe, it would probably be kilometers per hour. That's okay. You go into the grocery store later on today and you're going to buy some potatoes. Is there a rate involved? Dollars per pound? That's a rate, isn't it? Oh, so also with your car, you're going to have to fill up the gas tank soon because you're not getting a lot of miles per gallon. Those are rates. A rate is any time you have a quotient with two different units. That's what a rate is. Oh, miles divided by gallons. Or it could be miles divided by hours. Or it could be dollars divided by pounds. That's what the word rate means. You have a quotient of things of different units. A percentage is almost exactly the same thing. A percentage is like a rate, but a percentage is a quotient of two things with the same units. A lot of people don't realize that. I have people in calculus who don't realize that's what the word percent always is. That's why when you say percent, you don't throw units on it. Oh, I got 87% would be I got 87 points per every 100 points. You're driving up to LA, let's say LA is 120 miles. You've driven 60 miles so far. So you've driven 60 miles per 120 miles. You've gone 50% of the trip, haven't you? We don't put units because it was miles divided by miles. So whenever you say the word percent, it's a unitless term because that's why it's called a relative rate. Relative because it's the same unit. Whenever you hear the term relative in a math situation, they're always referring to percent. Okay, it's the relative rate. So again, 87% on a test means the number of points you got relative to the number of points possible. Points part canceled. 87 out of 100, 870 out of 1,000, does it matter? No, it's still the same quotient. If I drove 50% of the trip, right, that means I'm halfway there. It wouldn't matter how many miles I'm talking about, I'm halfway there at 50%. So with a random variable, the important thing is the probability of each outcome. Not how many times it occurred, but just simply the probability. Now, how do I find probability in general? I want to make this clear because the formula we're going to develop is actually very, very simple. Very, very simple, but it's the formula we're going to always use in this context. Okay? Let's suppose that we wanted to practice our free throw shooting. Free throw shooting is a great one in statistics because it's so easy. You made it or you missed it. And your percentage is how many you made divided by how many you attempted, not how many you missed, right? Oh, okay. So let's just say, hypothetically, right, that Petra was out there and she made 80 free throws out of 100. And let's say this is highly representative of your true skill, okay? This wasn't a fluke, that wasn't a bad day. Well, this is equal to 0.8, isn't it? So if I said, what is the probability she's going to make a free throw, what would you say? It's 0.8. By the way, you never give a percent for probability. I want to make that clear. A lot of us get trained. We speak in percentages. You can't do math in percentages because you're always going to be off by a factor of 100. Always. There's no scenario where the percent, right? If I said 80%, you don't multiply by 80. You multiply by 0.8. That's why we say the probability is 0.8, and that's the number we use in calculation. So if I said, all right, Petra's going to go out and shoot 10 free throws, how many do you think she's going to make? 18? She's going to go out and shoot 10. I don't think she can make it. She's really good, but she's not that good. If she's going to go out now and shoot 10 free throws, how many do you think she's going to make? 8. Isn't that kind of the common sense answer? Because she makes 80% of them. Now, might she make more? Might she make less? Yes, but 8 would be the most likely outcome. Okay? And we're going to show later that mathematically that's the calculation. But what you did was you said, I believe the probability of success is going to be 0.8 based on what I've seen in the past. But where did you get the 0.8? You got the 0.8 because that's how many she made, that's how many she attempted. Her frequency, how many she attempted. Oh, so let's go back to, I said mu was the sum of each score over the number of scores. Wait a minute. Each of those x's, if I divide it by the n, that gives me the probability. So this is exactly the same. We talked about things, what if I have repeated outcomes? Right? We did that, remember we had 500 people take a 10-point quiz at UCSD. You know, we might have 130 people get the same score. You didn't add that score up 130 times, you just said 130 times that score. Agreed? It made it a little bit easier. So let's assume for a moment that we have potentially repeated values. So then I said, you throw the frequency in there. So if the first score happened 25 times, I don't want to add up the first score 25 times, I just want to multiply by 25. That's kind of the common sense thing, right? The second score happened 3,000 times. I don't want to go this plus this plus this 3,000 times. I just multiply by 3,000 times. But that means that this is the same as this. But this is the probability. This is her 80 over 100, in other words. That means in a random variable sense, where I'm expecting things to be repeated, we'll do a lot of examples, you'll see that. This is the same as just saying the sum of each score, and I'm going to use a little p, times its probability of occurring. Oh, that makes it so much faster. Because if I know the probability of the outcome, I don't need to know how many times something happened. So if I told you, hey, Petra makes 80% of her free throws, so the probability she's going to make a free throw is 0.8. Doesn't matter how many she shoots. That's the probability she's going to make a free throw. I have a fair coin. The probability of a tails is going to be 0.5. I don't actually have to flip it a bunch of times for you to see that. I know that's its probability. Does that make sense? If I know the probability, how many times I do it, it's not all that important. So, let me give you a situation. All right? So, in San Diego, maybe based on census data, we wanted to determine, okay, in a San Diego household, let's say we've used all San Diego households, which, by the way, there's a lot of households in San Diego County, right? There's probably in the million range of houses in San Diego County because there's a few million people. But I don't need numbers, I need probabilities. So what we did was we measured or counted the number of pets per home. Does anyone here have a pet? Does anyone here have more than one pet? Does anyone have more than, anybody have more than 3 pets? Wow, how many do you have?
I have 8 chickens and 2 cows.
Would you call chickens a pet? Yeah, I don't know if I would call it, I don't know if chicken's a pet, but yeah, I'm mostly dog. Okay, let's make it simple. Let's say we're talking dogs and cats. We'll just. So let's say, hypothetically, we went around and we found that in San Diego County, X will be the number of pets in the home. Okay? And so the possible values for X would be as follows. 0, 1, 2, 3, 4. Let's just say we found that nobody had more than 5. Okay, just whatever. Now, I want the probability of X. I don't need to know how many homes had 0 pets. I want to know what, think of it in terms of percentage. What percentage of San Diego homes had 0? That would tell me its probability. So let's say the probability of 0 was, how about 0.09, 1 was 0.32, 2 was 0.26, 3 was 0.18, this was 0.10, and this was 0.05. Okay, I'm just making up the numbers. So in San Diego County, the probability of a home having 0 pets is 0.09. That would be 9 out of every 100 homes. Do I need to know how many homes I'm counting? No. Remember when I talked about percentage being relative? So if you told me your percent on the exam, do I need to know how much the exam was out of? No. Do I need to know your actual score? No. I know how you did on the exam. If you know, you told me you got 100% on the exam, yeah, but how much was it out of? Would that really matter? No, I got everything right. Whether it was out of 1 point or out of 1 million points, I got all of them. Knowing the percentage is so much more useful, in other words, in that case. So you could read this way. 9% of the homes in San Diego had 0 pets. 32% of the homes in San Diego had 1 pet. You can think of it that way. But I need the decimals, I need the probabilities. So if I said, what is the average number of pets in a San Diego home? Well, don't I need to know how many had 0 exactly, how many had 1 exactly, and then divide it by? No. I just have to do this. This is so much faster and so much easier. So let's do this for this problem. Let's find the mean, and here's what the mean is. The mean is 0 pets times its probability, plus 1 pet times its probability, plus 2 pets times its probability, plus 3 pets times its probability. So get out your calculators, please. Plus 4 pets times its probability, plus 5 pets times its probability. So if these numbers were actually accurate, this is a population, because I'm talking about all of San Diego County.
.03.
2.03, any confirmation on that? Did you get 2.03? Okay. 2.03. What does that mean? That means in San Diego County, the average number of pets per household is a hair over 2. Oh, okay. Now, we give this a very special name. Because I was working with a random variable that represented the number of pets in a home and then its probabilities, if I said, we're going to randomly select a home in San Diego, how many pets do you expect them to have? 2. You expect them to have 2. Does that mean they're going to have 2? No. That's the most likely outcome by a lot. So we call this number the expected value of X, and we give it a really, really handy way of writing it. We call it E of x, expected value of x. The expected value of the random variable is the mean. But we use different words. Why do we use different words? You're going to flip a coin 1,000 times. How many tails do you expect to see? 500. That's the same as if you actually did it and we calculated every probability and calculated out the mean would have been 500. But in words, if I said, how many do you expect? Doesn't that work a little better in your brain? It doesn't sound so mathy. All right, this week there's a 90% chance of rain, in which case we'll lose all this money. There's a 10% chance of sun, in which case we'll make all this money. What can we expect? Okay, you're actually calculating the mean. But we use words like, what can we expect? Does that mean that that's what's going to happen? Does anybody anybody a football fan? Who's favorite tonight?
I think it's the Chargers.
I think they're playing Kansas City, so probably the other guys. But, okay, give me a number that you think they're favored by.
3.
3. So what does that mean in simple terms? That means the Chargers are expected to win
5 field goals.
by 3 points. Does that mean that's what's going to happen? No, it means it's the most likely outcome. Does everybody see that? Oh, okay, that's all it means. So if you're a gambler, you say, yeah, I think they're going to win by at least that many. I'll put money on the Chargers. Or you say, I don't think they're going to win by that much, so I put money on the other team. Those are only 2 choices, right? You don't put money on both. That'd be a bad idea. So the expected value is actually the mean. But in language, it makes more sense. If the average number of pets in a San Diego household is 2.03, then if I grab a random household, I expect them to have 2 pets. And another way of saying it, now if I could take every single household in San Diego and average the number of pets, that's exactly what we just did. But I don't need to know how many households, I need to know the relative frequency. So let's draw a picture, let's draw a histogram to remind us, because a lot of times, I'm going to need this in a minute, because you guys are going to tell me what it is. A lot of times when we're doing the histogram, we forget what's the point. The histogram is the simplest part of the problem. It's a simple visual representation of the data that's sitting in front of us. Because when I look at this, everything here is accurate, but I just see a bunch of numbers, right? It's like the Matrix movie, right? You just see a bunch of symbols. Do you have a feel? I don't know. What are my possible values? 0, 1, 2, 3, 4, 5. 0 should not ever be on the line here because it's got its own rectangle. What is the highest probability you see? 0.32. So should I put, like 1 and then put 0.32 down here? No, I mean maybe like this, 0.1, 0.2, 0.3. In other words, spread it out so you can actually see it. Okay, so I'm going to do my best, because I don't have a straight edge in front of me, but if I'm drawing this picture, I'm just making it. All right, 0.09, just short of there. Let's say about there. 0.32, a little past that guy. 0.26, be about right there. 0.18, maybe about right there. Obviously, if you have graph paper, this makes it really easy because you got all the lines already there. 0.10 out here, and 0.05. Here's a simple visual that says exactly the same thing that does. Now, here's one of the cool things about this is called a relative frequency. I didn't tell you how many times we got 0. I said it happens with a probability of 0.09. That could, what if there's only 100 homes in San Diego County? Then it means it happened 9 times. What if there's 100,000 homes in San Diego County? Then it happened 9,000 times. What if there's 1,000,000 homes in San Diego County? Then it happened 90,000 times. But the problem with knowing how many homes, I have to know too much information. It's so much easier if I just give you the number, isn't it? I don't have to do any divisions and calculations. Now here's the other great thing about the relative frequency. What is the width of each rectangle? 1. It's a width of 1 unit, agreed? What's the height of each rectangle? its probability. Therefore, what's the area of each rectangle? Well, isn't the rectangle's area base times height? So the area of the rectangle is equal to the probability of the rectangle, isn't it? If this is 1 unit wide times 0.1, then the area is 0.1. So here's one of the great things about this type of problem. The probability is equal to the area. Therefore, my areas will always add up to 1, because that's the total probability. By the way, that's extremely convenient and useful, and we're going to use that a lot in the future. If all the areas add up to 1, right, then the area and the probability are exactly the same. So if I said, well, what's the probability of being, excuse me, 4 or more pets? Well, I just add these up. What's the probability of being fewer than 2 pets? Well, I just add these up. It's fairly simple. So we have a simple visual. That's the easiest part. We did the calculation, which just wasn't all that complicated. Now the trickiest one, we're going to do the variance. We're going to do this one. But remember, let's assume we have repeated values. So you're not going to take the score, the 0 squared plus 0 squared plus 0 squared plus 0 squared. No, you're going to multiply it by the frequency. So I'm going to throw in the frequency here, little fi. Assuming that scores are repeated. What if scores aren't repeated? Then what is the frequency? 1. Does that change the formula at all? Not at all. But would any of you write everything times 1 plus times 1? No, you wouldn't bother writing it. So if we were talking about, you're going to take a 600-point exam, there's 30 of you. Do you think we're going to have a lot of repeated scores? Do you think it's possible we don't have a single repeated score? Is that possible? Sure. We have 500 people at UCSD taking a 10-point quiz. Are we going to have repeated scores? Yeah, we're going to have scores that happen hundreds of times. That's when you consider frequency, because you already know you're going to have repeated scores. In this class, no, everything's probably going to happen one time, no big deal. So in general, if I've got this just like the other one, this ends up being the following. Frequency over n is the same as the probability. So I'm removing the quotient. I'm saying just multiply it by its probability of occurring. Then what? Minus mu squared. Turns out this is the most useful and by far the most common. Variance is calculated usually not by taking every score into account, but by taking the probabilities, because you have so many possibilities. Now, we have another name for this guy. If the mean is the same as the expected value of x, then the variance is, we call it the variance of x, and we write it this way, VAR. It's the variance of the expected value. It seems kind of redundant, like we're repeating ourselves. But remember, when you're talking in words, and I say, well, what can you expect? You expect the mean. What's the variance of what you expect? You see, that's why we use those words in that notation. It's the same thing. So let's take the example we just did, and let's calculate the variance of this. The variance calculation is going to look real similar to the mean calculation, but I'm squaring things. So in this case, I'm going to write VAR of x, which is the same as sigma squared, is equal to okay, 0 squared, I'm going to write it out, I know it's 0. 0 squared times 0.09 plus 1 squared times 0.32 plus 2 squared times 0.26 plus 3 squared, what is that, 0.18 plus 4 squared times 0.10 plus 5 squared times 0.05. Is that the answer? Almost. The only common error that anybody ever makes when they're doing this is they forget to do that. So what am I going to subtract? 2.03 squared. Now let's do this calculation. I said it's going to look real similar. Why? Because I'm using all the same values. But now I'm doing the sum of the squares times the probability. Let's say we have 1 million homes in San Diego County. I think that's conservative. We might have more than that. I have 1 million homes in San Diego County. Do you really want to literally deal with 1 million numbers to do this? Oh, heck no. I'd rather do that. It's so much easier and so much faster. So let's do this calculation. It's each squared score times its probability, and then in the end, subtracting the square of the mean. Okay, tell me when you have a number.
Negative.
Shouldn't be negative. Shouldn't be negative. Does anybody have a number? That's what I got. So our minds are becoming one. That's scary. You start dressing like me soon. You don't want to go there, by the way. So what you got? Read it out to me.
1.7091.
Anybody else get that? Good. That just means we hit all the right buttons. Now, that's the variance. What number do we actually use when we describe things? We usually use the standard deviation. So what's the standard deviation? Well, it's the square root of that number. Okay? The standard deviation is the square root of that number. So what is the standard deviation? What is sigma? Well, it's going to be this. So let's take the square root of that. And that's about 1.31, 2 decimals. We're saying for San Diego County, the mean number of pets, expected number of pets I would have in a house is about 2, and the standard deviation is about 1.3. Do you remember the range rule of thumb? What was the range rule of thumb in words? The vast majority of all outcomes are within 2 standard deviations. Now, if the standard deviation is around 1.3, then 2 standard deviations would be around 2.6. 2.6 would actually put me in the negative, so I've covered everything at this end. And if I add 2.6, it'd put me at roughly 4.6. So what's the only thing I didn't count with the 5s? Have I got almost all outcomes? Yeah, simple math. I've got 95% of all the possible outcomes came within 2 standard deviations. That's a good thing, because that's what the range rule of thumb tells us. It's called a rule of thumb. It's not an absolute formal mathematical law. There are always exceptions, but what we're saying is, hey, if I did it right, almost all of the outcomes are going to be within 2 standard deviations of my mean, and we did do it right, and that's what we just saw. That's a good thing. So, the random variable is what you're actually counting, and it's a discrete value because you're counting the number of times that occur. Then you're finding the relative frequency, and you're doing all this stuff. Now, a lot of times you're given the information. It makes it a lot easier, okay? So, one of the census data. You've all heard your whole lives, the average American household has 2.2 children. How many have ever heard that statistic? I've heard that my entire life. By the way, I don't think it's true anymore. I think it's less than that. But we've been hearing that, and you're going, okay, who's the 0.2, right? How do you have 2.2 children? What does that even mean? Well, it's the average number. That's like saying if I took 10 households, there would be 22 children. Oh, okay. Some households might have a little more, some have a little less. It's the average. The average doesn't have to be an attainable value. If I give you the average test score, it's probably got a decimal on it. And nobody scored a decimal outcome, did they? If I said the average age of the group, it might be a number that nobody actually is. But it's somewhere in the middle. So the average it's okay for the average to not be an outcome because it's probably got a decimal value. So if I said, how do we compute the average number of children in a household in the United States or California or San Diego? It's the exact same thing. So change this from pets to children. Oh, in fact, let's think of this as children now. Let's just say hypothetically, there are no Catholic families you know, in San Diego. It's a joke, right? So therefore, there's no really large outcome. My grandmother was Catholic and she was one of 13, so that was more the norm. So let's just say hypothetically in San Diego County, 5 was the most. We know that's not true. Let's just pretend it is. And this is the number of household, or the probability that you had 0 children, 1, 2, and so on. Then what would we say? The average number of children in a San Diego household was 2.03. It's the exact same thing. This is what the census data is, though. So they've taken every household in the United States. They're not sitting there adding 1, 1, 1, 1. They're saying, no, what is the probability of none? Or 1, or 2, or 3, or 4. Now, in actuality, that can keep going, can't it? The 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Is there a highest number of children that you are allowed to have? No. Is there a highest number of children that somebody does have? Yeah. It's like saying there was a highest income last year. There was a highest housing cost last year. But is there an actual ceiling to these numbers? You know, in sports they call it a salary cap. Is there a child cap in the United States? No. Is there an income cap in the United States? No. There's always a highest income, but can't it be higher next year? Is there an age cap? Ooh. Is there an oldest person in the country? Yeah, there's somebody who's the oldest person in the country. Can they be older? Are they allowed to live another year? Sure. There's an oldest person, but is there an upper limit? Nope, can't live past that. That'd be a scary movie, wouldn't it? We're going to have an age cap now. No, so the idea is that, yeah, I can have a lot more, but it doesn't go forever. There is a highest one, and then I would have the probabilities, and I would calculate it that way. This type of calculation is so much easier. It is so much easier to do this. If you know the probability of the outcomes, then all you got to do is multiply the number by its probability and add them up. That is one of the fastest calculations, and that's actually the way it's done in reality. We don't typically deal with every single outcome because, remember, we have a big country. Heck, we have a big campus. So let's suppose every one of you took some sort of exam. Keep it simple, like a true-false multiple choice test, where there's no partial credit, you got it right or you didn't, and we just tallied right answers. That makes it easier. I'm just going to count how many right answers you got. And now we want to talk about, okay, what was the probability? You got 0 right, you got 1 right, 2 right, 3 right, 4 right, all the way down the line. And then we could say, here's the average number of right answers. But 20-some thousand people took this test. We're not going to go, okay, 0 plus 1 plus 1 plus 2. That would be very impractical, wouldn't it? Okay, so that's a situation where this is useful. Now, we're going to get into a gambling situation. Okay, because expected value is exactly what you're doing when you're gambling. You're a gambler. And there's a couple of different ways you can think about this. I'm going to a casino, and I'm going to play a game of cards, or I'm going to play a roulette wheel, or I'm going to do a slot machine. My probability of winning is actually known ahead of time. There are measurable probabilities of winning. Now, am I going to win in the long run if I continue playing over and over and over and over and over again, in all likelihood? No, because if I could win, if in general a person is going to win more than they lose in the long run, then the casino couldn't stay open, could it? They'd go broke really, really fast. No, in the long run, on average, you're going to lose most of the time. Okay, it's that simple. Will certain individuals win? Sure, but the overall average, the expected outcome would be that you lose most of the time, because otherwise, again, they can't stay open. So we're going to play a game of chance, but it's going to be different than chance. We're going to play against each other. Okay? We're going to play against each other. We'll do something simple like you take a die, one single die, and we're going to roll the die. Make it really simple. We're going to roll the die. Okay, everybody all right with that? I'm going to roll the die, and here's how it works. If you roll 1 or 2, you get $20. If you roll 3 or 4, you get $10. If you roll a 5, you pay $15. And if you roll a 6, you're going to pay $30. We're playing against each other. Okay, so you roll a 6, you gotta give me $30. You rolled a 1, I gotta give you $20. Would you play this game? This is not an easy question, is it? There are ways you can win, there are ways you can lose, agreed? So what we're gonna do is calculate what is the expected outcome. You're gonna play one time, what is the expected outcome? And the easiest way to think about this is, if I play one time and I find the expected outcome, then that means if I play a whole bunch of times, it's like starting over every time. Let's just say the expected outcome is that I win $2. Then if I play 1,000 times, I should expect to win $2,000. If the expected outcome is that I lose $1 every time I play on average, then that carries forever and ever. That's how all games of chance actually works. The probability of you winning and losing doesn't change the next time you play, okay? You've heard the term gambler's folly. That's exactly what that notion is the thinking that, well, I've lost a whole bunch in a row, I've got to win. You know that die I'm rolling? It doesn't have a computer chip in it. It's not keeping track. It starts over every single time. So, let's call, let me erase this. Let's call let's call X the amount you win or lose. Okay? What are my possible outcomes? So we often write it in set form. I can win 20. What else?
10,
I can win 10.
negative 15.
Good. I can lose 15, or I can
Negative 30.
lose 30. Are all of these equally likely? Are you sure? There's only one way I can lose 30. How many ways can I win 20? 2 ways. How many ways can I win 10? 2 ways. Oh, so they're not equally likely, are they? So what is the probability of each outcome? Well, how many faces are there on a die? There's 6. Assuming that the die is fair, right? And a 1 is just as likely as a 3, is just as likely as a 6, then what is the probability? I'll put the probability right under it. What's the probability you will win $20?
2 out of 6.
2 out of 6. 2, 6. There's 6 possible rolls of the die, and 2 of them you win 20. What's the probability you're going to win 10? 2 out of 6. What's the probability you're going to lose 15? 1 out of 6. And what's the probability you're going to lose 30? 1 out of 6. Add up those numbers on the bottom. What do they add up to? 1. Is that a good thing? Yeah.
Yes.
If they don't add to 1, we have a problem. We're missing an outcome, or we have something double counted. My probabilities add to 1. That's good, because we've just covered every possibility. So I would like to know, we're going to play this game one time and one time only. What can you expect? Okay, so we write it this way. The expected value of x, which is the same as mu, is 20 times 2, 6, plus 10 times 2, 6, and you can put the dollars in there, you know, because my answer is going to be dollars, plus negative 15 times 1/6 plus negative 30 times 1/6. Now let's add all those up. What does it come out to be exactly? Or does it come out exactly? .5. Does anyone else get that? So this is equal to, let me write it this way. $2.50. Now, is $2.50 a possible outcome? You can win 20 or 10, lose 15, lose 30, and your expected outcome is that you're going to win $2.50. But you can't win $2.50. Yeah, but you also can't have 2.2 children. That's the average outcome. So here's an easier way to think about it. There's 30 of you. We're all going to play this game one time. Some of you going to win, some of you going to lose. But the group average is going to be $2.50 winnings. Does that make more sense if you think about it that way? Okay, I'm going to play this game 100 times. That means I should expect to win about $250. So the expected value, like I said before, doesn't actually have to be an outcome. It's the average. Now, do you want to play this game? Of course you do. Why? Well, why do you want to play this game?
Because you're gonna win $2.50.
Because on average, you're going to win. Now, if this were a casino, this number is probably going to be negative. It's not going to be a big negative number, but it's definitely going to be a negative number because you have to lose more often than you win. Your average overall, or the average of all the people, has to be negative, like we said. Now, what if I flip this around? This is what you're going to pay me, this is what you're going to pay me, this is what I'm going to pay you, this is what I'm going to pay you. Then the expected value for me is $2.50, but what is it for you? If it's positive $2.50 for me, what would it be for you? Negative $2.50. Now, do you want to play this game? No. What game, tell me an outcome that would make everybody want to play. Because in other words, we're playing versus each other. If your expected value is positive and mine is negative, I'm not going to play. Who would play that game? We're playing against one-on-one. Okay, I'm going to play LeBron James in a game of one-on-one later today for, $1 million. Yeah, that really won't work, will it? Wait a minute. First 1 to 20 baskets wins. What if I get to start with 19 baskets? Do you think maybe there's a chance I could make 1 before he makes 20? Maybe. Yeah, you haven't seen my skills. No, think about that. Would you say, first of all, there's no way you take that bet originally, but what if I said I only have to make 1 before he makes 20? Now all of a sudden you're saying, that I just evened up the playing field. You said the Chargers are favored by 3 tonight.
Actually,
Because-
the Chiefs are favored by 4.
Okay, the Chiefs are favored by 4. Okay, that means that the expected outcome is the Chiefs win by 4. And you'd say, well, then if I'm a betting man, I'm betting on the Chiefs. What if I said the Chargers get to start the game with 4 points on the scoreboard before the game starts? If the expected outcome is the Chiefs are going to outscore them by 4, haven't we just created a tie as the most likely outcome? Now all of a sudden, if you're a betting person, you'd say, I could go either way. Are you getting my point here? If I'm playing LeBron James, he's going to destroy me. But if I get to start with 19 baskets, now you're saying, you know what, Mr. Brown might make a basket. There's a really good chance that I could make 1 basket before he makes 20. And now all of a sudden you go, I've just sort of evened up the playing field. This is what is called a fair game. This is actually a mathematical term. A fair game is one where you both are equally likely to win. So in other words, in a fair game, do you know what the expected value always is? 0. Does that make sense? Oh, so nobody has an advantage. So if we're talking sports and you say the Chiefs are favored by 4 points, they're saying, we believe the Chiefs are slightly better. So you go, well, I'm obviously going to bet on the Chiefs. No, you have to bet on the Chiefs and give up 4 points. Meaning the Chiefs have to win by more than 4 points for you to win your bet. Oh, because we're saying we believe they're a little bit better. This is how much better we think they are. So if the Chiefs only win by 1 point or 2 points, it's as if the Chargers won the game. Because remember, we let them start with 4 points. Does that make some sense? That's how it works mathematically when it comes to the gambling aspects of sports. If one team is favored. Now, What if it literally was even? I can't pick a winner. I think they're literally even. Well, then nobody has an advantage. Right? That would be a fair game. I'll use college football for an example. I always love it because, Alabama loves to schedule games early in the season. They'll schedule a couple junior high teams. They'll schedule weak teams. And then you'll look it's not unusual for them to be favored by 30 points or 40 points. They had 2 games last year, I think, where they were favored by over 40 points. Yeah, that's a fun game to play, and I'm sure. Well, what if the other team makes it close? By the way, I watched the Texas-Alabama game last week. Did anybody see that game?
Yeah.
Alabama won on the last play of the game field goal, and they shouldn't have won. They got a break on a really terrible call by the referee, who obviously had money on the game. Alabama won by 1 point. Do you know they were favored by more than 20? That means every single human being on planet Earth who bet on Alabama lost a lot of money. And every human being on planet Earth that bet on Texas won a lot of money. But Texas didn't win. But they didn't lose by 20. They lost by 1. They should have won the game. That was, by the way, Texas not only should have won the game, they played the entire game with the backup quarterback who was injured. The backup was injured, and then the center got injured. So they played a game, it's sort of like saying they played a game with one hand tied behind their back, and they still almost won. The point is, Bama was a 20-point favorite, and they didn't win by 20 points. So you don't bet on Alabama, you bet on Alabama, and they have to win by this much. So again, to make it a fair game. That's basically me playing LeBron James. Alabama with the big point spread. So they're saying, we're going to give the other team 40 points to start the game, and then let's see who wins the game. That's kind of what we're saying. So a fair game is any game where the expected value is 0. I want this to be a fair game now, because I want everybody to want to play. Right now, it depends which one you are, right? You want to be this person, you don't want to be this person. So I'm going to take that number off the board. And I want you to tell me, what does that number have to be for this now to be a fair game? It's a good question, isn't it? We're not going to change the first one. Nope. You're going to get 20 bucks if you roll a 1 or a 2. You're going to get 10 bucks if you roll a 3 or 4. You're still going to pay 15 if you roll a 5. What are you going to have to pay if you roll a 6 to make this a fair game? It's not that complicated.
15.
Well, it'd probably have to be more than 30, wouldn't it? In other words, 30 wasn't enough. Let's do it this way. I need this to be 0. Well, right now, what do you have? You have 40 plus 20, that's 60 in your numerator, minus 15, minus,
32.50.
no,
45.
45. 40 plus 20 minus 15 minus 45. Will 45 do it? Put it in your calculator. Let's see.
That's what I did.
If I put, where is it? If I put $45 here, will I now get a 0? Yep. That was the right answer. All right? How many have ever bought a raffle ticket? For anything? I remember buying one a few years back. They were giving away a car. It's like, and the raffle ticket was like, it was, by the way, usually raffles are fundraisers for something. It was at my kid's school. And somebody had donated a new car. They didn't go out and buy a new car. Somebody donated a new car, which is unreal. And they were raffling off the new car to raise money for the school, which is really a good idea. Now, I want to hold a raffle to raise money for, the Mesa Math Department, whatever you want to think. A raffle is still a game of chance, isn't it? Are you gambling when you buy a raffle ticket? Absolutely. It's a form of legalized gambling. People don't realize that. You're paying money hoping to win big. That's called gambling. But it's legal gambling. It's absolutely above board legal, and it's, you think about it for a good cause. Do you want your raffle to be a fair game? You're gonna hold the raffle. You wanna do this as a fundraiser for your organization, you know, the math department is your organization too. Do you want the raffle to be a fair game?
Yes.
You say no, why?
If it's a fair game, you lose money.
Or you won't make money. In other words, if it was a fair game, you're going to break even. Then what was the point of having the raffle? In the end, we broke even. In other words, we didn't make a penny. We didn't lose any money, but we didn't make any money. So a raffle, you don't want a raffle to be a fair game because you want the raffle to make you money. Oh, so if we hold a raffle, we want to make money. Now, when you buy the raffle ticket, you know the probability of winning is not great, right? You buy, maybe 1,000 tickets were sold, you bought one. So you got a 1 in 1,000 chance. But the prize might be so good that you say, you know, it's worth it. I paid $20 for a raffle ticket for a new car. I could afford the $20 loss. It didn't, you know, mess me. I was able to eat that week. But I could have won a new car. It was worth it to me. And by the way, it went to a good cause. I convinced myself that it wasn't a bad expense. I'm going to buy a lottery ticket for $20. Again, I'm more likely to be struck by lightning 3 times in the next 5 minutes than win. That was $20 I just threw away. That, to me, and it doesn't go to a good cause in that case. So I'm not buying the lottery ticket, but I'm going to buy the raffle ticket. So we're going to have a raffle, and we're going to compute the expected value. So in a raffle, but this is a different type of raffle. This is a money raffle. Now, this is interesting. At my wife's high school, at football games, they do something really interesting. They have fundraisers all the time. They will do a really fast money fundraiser almost every game at halftime. They'll say, you buy a ticket, I think it's like literally $1. You're gonna buy a ticket for $1, and you're gonna put your name on it. And there will be a few $100s, and what they do is at halftime, they'll draw a name, and you get half that money. Now, would you buy a ticket for $1 if you might win $100, $200 for $1? Yeah, and by the way, it's fundraiser for the school. It's a raffle, but it's like the simplest, fastest raffle you've ever seen. So they go around the stands and everybody's buying a $1 ticket. And so maybe $300 in literally 15, 20 minutes, maybe $300 were just spent. So then at halftime, they pull a name out of the hat and they give them $150. Cool. You just got $150 for a $1 ticket, but what's more important is the school got $150 for fundraiser. Now, it's not big money, but it's easy money, isn't it? That is a raffle. That is an absolute raffle. That is legalized gambling. You know, they have to report it on the taxes and stuff like that. So we're going to hold a raffle, and, okay, we'll make it a little simple. We'll say 1,000 tickets. I don't want some weird number, you know, because then I have weird denominators. 1,000 tickets are sold for, let's say, $2,000 each. This is an expensive raffle. Okay? 1,000 tickets are sold for $2,000 each. There's one first prize, and the first prize is $1 million. So you say, I might want to do this raffle if I can afford the $2,000 ticket. There's going to be 2 second prizes, and they are going to be, let's say, $100,000. There's going to be 3 third prizes, and they're going to be, let's say, $50,000 each, and then let's say there's going to be 100 consolation. You've heard that term before? Consolation prizes. This is the participation trophy. Okay? And they're going to be $1,000 each. So in all, 106 people are going to walk away winners. So the question is, you're going to buy a raffle ticket. What is the expected return? Your expected return is not gonna be one of those outcomes, but it's gonna basically be the average of everybody who just bought a ticket. You understand? There's 1,000 tickets that were sold. Most people aren't gonna get anything. Some people are gonna, huge. What is the average outcome of all 1,000 people? That's what the expected value is. Now, one of the things that people don't always remember to do is take this into account. You see, the consolation prize if you won $1,000, are you walking away $1,000 richer? No, because you had to spend $2,000 to get the ticket. Oh, does that make sense? Yeah, you got to take into account the fact that you had to buy the ticket. And the raffle tickets weren't free. So if I said, at the end of this raffle, what are the possible outcomes a person could have? Remember, 1,000 people each just spent $2,000 on a ticket. So if you win $1 million, so X will equal the winnings or losings. Losings, is that a word? The winnings or losings of each person, losses, I guess. So if you won $1 million, what are you walking away with? Not $1 million, because you had to spend $2,000. So what are you walking away with?
998,000.
998,000. Everybody got that? Oh, because I had to buy the ticket. If you don't take that into account, then you're going to have a huge error in the answer. Now, you won $100,000, but you had to buy the ticket. So that's 98,000 you'd walk away with. The next person, third prize, you won $50,000, but you spent $2,000 to get the ticket. So you walked away $48,000 richer. Now, your consolation prize, you got $1,000, but you had to spend $2,000. Negative 1,000, good. Is that it? No. How many? That's 106 people. 1,000 tickets were sold. How many people got nothing? How much? 890. 894. One of these, two of these, three of these. Do you agree that 894 people walked away with nothing? And by the way, all of those people had to buy a raffle ticket. Oh, so 894 people just lost $2,000. They bought a raffle ticket and they didn't win. By the way, isn't it the vast majority of people? You bought the raffle ticket, you didn't win. Yeah, that's how we make money. Now, what is the probability of each of these outcomes? Well, 1,000 tickets were sold. There's one first prize. What's the probability you're going to win?
1 in 1,000.
1 in 1,000. Yeah, it's really not that complicated. That's pretty easy. There's 2 second prizes. So what's the probability you're going to win this? 2 over 1,000. There's 3 third prizes. You're going to be 3 over 1,000. There's 100 consolation prizes. 100 over 1,000. And how many people didn't win anything, you said? 894 over 1,000. And quick check, if I add up the probabilities, that they better add up to 1. 1 plus 2 plus 3 plus 100 plus 894 is 1,000. Good. Can we calculate the expected value now? Yeah. What are we going to do? This times this plus this times this plus all the way down the line. So everyone, let's do that. Let's all calculate the expected value. Tell me when you get a number.
That's 550.
You got negative 550. Did anyone else get that? He says his answer is, and that would be dollars, by the way. Did anyone else get that number?
Yeah.
What does that mean? There's a raffle, $1 million first prize. Whew. But it's an expensive raffle ticket, costs you $2,000. The expected outcome of every single person who bought a raffle ticket is to lose $550 in the long run. That's actually correct. By the way, that's all raffles would be that way. Should you buy a raffle ticket? It's a tough question. I believe it's going to a good cause. I have money set aside, blah, 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 blah. Yeah, that's fine. But if you couldn't afford to buy the raffle ticket and you had to borrow the money to buy the raffle ticket, should you buy it? Well, if the expected value is negative, that means, well, most people come away with nothing. Here's another way of thinking about that. 1,000 tickets, $2,000. That means $2 million were taken in. But significantly less than $2 million was paid out. Right? So the people holding the raffle made some money. How much money did they make on average? $550 per every person who played. So the average outcome, you didn't win anything, you got a consolation prize, you didn't win anything, you got the $1 million. Somebody's going to win. Most people aren't going to win, but the average outcome is to have lost $550. We could make this a fair game. We could increase the prize money, but then that kind of defeats the point of the raffle, doesn't it? So I don't need a raffle to be a fair game. Now, I had a great problem I asked this a number of years ago. I created a raffle situation where this was a positive number, which, by the way, has never happened. I called it the philanthropist raffle. You've got a philanthropist who wants to have a raffle, and they made way more of the big prizes, and now all of a sudden you had a positive expected value. Now this is a difficult question. Should you play that raffle if it has a positive expected value? Ooh, this is a tough one. I talked about the I-bonds earlier today. An I-bond has you actually have an expected value at the end based on what the likelihood that inflation is going up and down and all these things. And in the end, I'm watching. It's a financial advisor guy. It was an article, and then I'm watching the explanation, and he basically says, in short, he says this is a great investment if you can afford not to have the money. Because I think you have to start with like $5,000. It's like you have to start by buying it, or maybe it was $10,000 for these particular types of bonds. And you can make a lot of money. Should you buy this bond? Well, first of all, you can't touch it for 3 years. There's no guarantee of the return, And should you buy it? Well, it could be a great return, but only if you can afford to live without that money. Does that make sense? If I got to borrow the money to buy it, it's a bad idea. So I have the philanthropist raffle. Still it's $2,000 for a ticket, but the expected value now is positive. Should you buy it? If you can afford to lose the $2,000, yes. But if you can't afford to lose the $2,000, then the answer is still no. Yeah, but I have a really good chance of walking away with money. Yeah, but you're more likely not to win, right? Even if I upped the dollar amounts here, what if I made this, $500,000? I made this, $250,000. I up the dollar amounts to make this positive, but I don't change the probabilities. Might have a positive expected value, but you're still probably going to lose. And so that's something a lot of people don't take into account. That's why, again, people who gamble sometimes don't take these sorts of things into account. That, boy, I could win big. Yeah. I could win big at that slot machine. But the probability of me winning big is really small because it might only be, 1 in 1,000 or 1 in 1,000,000. There's one that I play all the time. Does anyone know what Publishers Clearinghouse is? It's where you buy your magazines. I mean, I bought my Sports Illustrated from there for many, many, many years because they were way cheaper than anybody else. And because I bought magazines, and that was the only magazine I'd ever buy, occasionally I'd give a magazine as a gift for somebody, a year subscription. It's actually a really good subscription place because it's cheaper than almost everywhere else. But they have giveaways a few times a year. Like $1 million or $5,000 a week for the rest of your life. They do this all the time. But you don't have to buy anything. So I always fill it out and send it in, and it costs me the stamp, that's all it costs me. And people are thinking, gosh, I have a chance of winning. And then you look and it'll say, probability of winning, it's usually somewhere in the neighborhood of 1 in 300 million. That's not really a good probability, right? If I had to count on that, you know, I gotta make my bills next month, I'm counting on winning that. When it says it's 1 in 300 million probability of winning, somebody's going to win. Somebody's gonna win. But 1 in 300 million is really not a good probability, but it doesn't cost anything to play. So I always do that one. Okay, I always do that one. So that, you know, because it doesn't cost me. But if it cost me money to do it, I wouldn't do it, because now it's just like the lottery. I'm paying money for something that I literally have almost no shot of winning. That's not a good investment at that point. So expected value, I'm giving you a glimpse. This is how things are actually calculated in real life, but the calculations are way simpler, aren't they? Because I'm not dealing with as many numbers as we were before. I'm dealing with probabilities of outcomes. That's a way faster calculation, and it's actually fairly easy to read. All right, let's go. Can you hit the button to stop it? I think it's on top. You're here to BPP.
Where?
Yeah, straight down.
Straight down?
Yeah. Oh, no, the button, I mean, press it. Oh.